Have you ever typed something into a computer, hit enter, and just wondered what happens next? I mean, really happens. How does an idea in your head, written in a language that makes sense to us, turn into an actual physical action inside a machine that only understands electricity? Well, that's the journey we're about to take. So yeah, that's the big question, right? It's this incredible trip that starts in the world of human ideas and travels down through all these different layers of translation, all the way to the raw physical reality of a processor. And even begin to understand this, we have to start with what I call the Great Divide. There is this huge fundamental communication gap between how we as humans think and how a computer actually works. I mean, look at this. On one side, you have us. We live in a world of abstract thought. We can just say add 5 and 3. It's simple. But on the other side, you've got the machine's reality, which is just a constant stream of on and off electrical signals. We just represent those as ones and zeros. There's no meaning there at all. So obviously we need a translator. Actually, scratch that. We need a whole series of translators. The whole journey really kicks off with something called a high-level programming language. For our purposes, let's just use C as the example. It's a language that was designed to be pretty readable for people, but also structured enough that a machine can eventually figure it out. So this single line of code is our starting point. To any programmer, this is crystal clear, right? We're creating an integer, we're calling it results, and we're telling it to hold the value of 5 plus 3. But to the processor itself, words like int or result, they're complete nonsense, absolute gibberish. And that is exactly where our first translator comes onto the scene, the compiler. You can think of the compiler as this brilliant, incredibly smart program whose entire job is to start bridging that great divide we talked about. So, the compiler takes our source code, the stuff that we can read and write, and it starts the long process of converting it into something that's much, much closer to the machine's native language. This is really the first big step we take down the ladder of abstraction. And right here, this is where the magic happens. Our one single, high-level thought gets fed into the compiler. And look what comes out. It's been broken down into multiple, way more basic steps. Each little command is a tiny instruction that gets us one step closer to what the hardware can physically do. It's like taking a complex sentence and breaking it down into a series of short, blunt commands. We are getting closer to the metal. Okay, so what is this new language that our code just got translated into? It's called assembly. This is the next layer down. And it's where our abstract idea starts to make real contact with the physical hardware of the computer. You know, assembly is basically a human-readable version of machine code. Each one of these little three-letter words, these mnemonics like move or add, they correspond directly to a single binary operation that the processor was built to perform. This is pretty much the last stop on our journey that is still readable to us before it all becomes just ones and zeros. Now, to really get assembly, you have to understand the blueprint it was designed for, which is called the von Neumann architecture. This is the fundamental design of pretty much every modern computer. At its heart, it's got a processor, the CPU, and a single bank of memory that, and this is so important, holds both the program's instructions and all of its data. This whole system runs on just a few simple but really powerful rules. Everything, your code, your data, pictures of your dog, it's all just bits. And because code and data live right next to each other in the same memory space, well, that has some really profound consequences. The CPU just chugs along, executing one instruction after the next from a numbered list, unless something tells it to jump somewhere else. Okay, so we've gone from C down to assembly, and now we're talking about the basic rules of the machine. But why? Why does understanding this whole complicated journey actually matter in the real world? Well, it really boils down to two absolutely massive areas, performance and security. How fast your program runs and how safe it is from being attacked are both directly connected to these super low-level details. So, on the performance side, a programmer who really gets this stuff can make much smarter choices. They can organize data in memory in just the right way, so the processor can grab it way faster. Think of it like organizing your desk so the tools you use most are always right there. Just being aware of this can lead to huge speed improvements. But you know, the security side of things is even more dramatic. Let's take a look at a classic, famous vulnerability called a buffer overflow. This is what happens when a program accidentally tries to stuff more data into a memory container, a buffer, than it was built to hold. And remember how we said code and data are stored together? This is where that idea gets really, really dangerous. So here's how an attacker can exploit this. They send the program this huge chunk of data that they know is too big. It fills up the buffer, and it just keeps going, spilling over and overwriting whatever happens to be next to it in memory. And the most critical thing it can overwrite is something called the return address. You can think of that as the program's GPS, the little note it leaves for itself, telling it where to go next. By overwriting it, the attacker can change the destination. And this is the terrifying part. The attacker has replaced the program's legitimate next step with an address that they choose, an address that points to their own malicious code. Just like that, they've hijacked the program. They've taken control, simply by understanding and breaking the low-level rules of how memory works. So, there you have it. From a simple thought like 5 plus 3, we've traveled down through compilers and assemblers, all the way to the basic architecture of the machine itself. And we've seen why understanding that whole journey is absolutely critical if you want to build software that is both fast and secure. And that kind of leaves you with one last thing to think about. As our programming languages get even more powerful, as we have AI writing code for us, is this journey from human to machine going to get even longer and more complex? And what new challenges for performance and for security are waiting for us down in those even deeper layers of translation?